Okay, so you might be wondering why we have all these various addressing modes that we can use. I'm going to give you one example of the reasoning behind these various addressing modes and what the original purpose of them is, even though we're going to see they have other purposes later on in modern compilers. Okay, so let's look at an example piece of code. Here's a totally different example where, in this case, in main, we're creating an integer array. So an array of 8 integers in main here. And we're sending that array into this function called update, which is simply looping through every value of that array and grabbing it and doing something to it. And we're not going to worry about what that is. We're going to worry about this purpose of looping through this array. So here is that array, and we can see here the way I've colored things. The 0th element of the array is in yellow, the first element is in green, and each byte is shown here. So 4 bytes per integer in this array. And so in main, we declared this to have 8 integers in it. So basically the 0th element is here, the first is here, the second is here, and so on in memory. These are held in memory contiguously, and we'll see that later on as well. The way that the compiler might put together the instructions for this loop itself for accessing every element of the array is something kind of like this. So first thing we need to realize is that RDI holds the int array value. Now in C, what that means, when we declare this to be an int star, we know it's a pointer. And then when we just use the name of the array like this, what that means in C is that when we use the name of the array, it's equivalent to as if we had gone to the 0th element and gotten the address of it. So the use of the name of the array is equivalent to a pointer to the 0th element. So RDI at the beginning of this update function would hold the pointer to the 0th element of the array, because that's what int array is when we use it in code like that. Okay, so now we have the pointer to the 0th element. RDI is pointing up here now to the 0th element of the array when this update function here, the code for it, gets started. So now let's think about what the this loop might entail, and in particular this line of code in that loop. So we could have RCX hold I. So the compiler might do something like place 0 into RCX at the start of the loop. And then the compiler might decide that EBX is holding next val. And so here's next val here. And then each time through the loop, the element that's going to be grabbed from memory here and placed into EBX is going to be in these terms. So now let's start with the 0th element. So if RCX is 0, then basically we're going to take 4 times 0 plus RDI. So that's going to be RDI. So the first time through the loop, this integer will get moved into EBX. And then the the next step is to increment I here, which is in RCX. So if we increment RCX by 1, so it becomes 1, the next time through the loop, it's going to take 4 times 1 and add it to RDI. That gets us down to a pointer that would point right here to the first element of this array. And so this continues where RCX will keep getting incremented and therefore go by 4 bytes each time to go down and get each element of this array. And this becomes the primary reason that this kind of indexing was set up, was for the purpose of being able to skip 4 bytes at a time, 2 bytes at a time, 8 bytes at a time, or maybe even 1 byte at a time if it's an array of chars. And so this is the primary purpose of this type of indexing. And of course, we're going to see later on now how it is also used for other crazy purposes, just to do math. And so you'll see some interesting examples of this going forward. Now, one thing kind of interesting here is you might have been saying, well, why was I in the R register as opposed to, say, the E register, since it's declared as an int here? And this is really important to note because you'll see this in code going forward, that the reason we use the R's here is because this is a memory access. And so each part of a memory access inside of these parentheses must be 8-byte register names, because this, inside these parentheses, we're assuming we're using addresses to memory like this, and that we're computing a new address, which itself has to be 8 bytes. So all of this type of computation is done on 8-byte register names, and that's very important to note here. Okay, so this wraps up the example of why these addressing modes, and then you're going to see how these are used for other purposes as well going forward.